Okay. So I said this phrase yesterday and then I took it back. It's points of inflection. So let's talk about what they are and how to use them. And hopefully you'll see that what we're doing today, tomorrow, is very similar to what we did last week. So just makes it easier for you. Definition of a point of inflection. Blah, 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 blah. Let f be a function that is continuous on an open interval, and let c be a point in that interval. If the graph of f has a tangent line at this point c comma f of c, then this point is a point of inflection of the graph of f when the concavity of f changes from upward to downward or downward to upward at this point. Okay. So we have a couple pictures here on the side to kind of help you make sense of what that definition is. The key part that I want to literally highlight for you is this. If the graph of f has a tangent line at this point, then this point is a point of inflection, right? So we have to make sure that the point we choose has a tangent line at this point. So we kind of have a couple visuals next to it so we can kind of see it. So the first one is we have the black graph and then we have that tangent line. Notice how it cuts through the graph, but notice how it's like to the left of it. It's like going on, like the tangent line is underneath the graph and then it changes to being like over the graph. And if you notice, that's the same kind of behavior we have in the second graph where the tangent line is above the graph on the left side, but then it changes. Then the tangent line is underneath the graph after that inflection point. And the last one, we have a very interesting looking graph where we have a horizontal tangent line. So the graph changes from concave up to concave down. Notice how in this case, it's like if you literally took it and then you kind of flipped it over, it'd be very similar to what we saw in the second graph. So visually, that's how the point of inflection should look. But we have a theorem to help us with this, and theorem 3.8 states, if c comma f of c is a point of inflection of the graph f, then either f double prime of c is equal to 0 or f double prime does not exist at x equals c. So I want to make like an analogy to kind of help you make sense of the new vocab that's been thrown at you. If you're okay with what we did last week, this should be a very easy analogy to make. So f of f prime. So f prime of x. Well, no, I don't want to do it that way. I want to do it the other way. I want to say that the critical number is to f prime of x as the point of inflection is to f double prime of x, right? Because both a critical number and a point of inflection deal with the fact that they are values of x where their respective derivative is either 0 or their respective derivative does not exist. The only difference is a critical number refers to the first derivative, whereas the point of inflection refers to the second derivative. Okay? So as long as you keep that in mind, we're literally doing the same skills that, like, using the same skills that we did last week. So enough yammering, let's do some math. So we have f of x equals that, and I want to figure out the point of inflection, and I want to know, and I want to discuss the concavity, right? So I want to see when f of x will be concave up, when it will be concave down, and is there a point of inflection? If so, where? So I chose this one because this is a rather tedious problem to do, so I want to make sure you see me work through it, so that way you can ask questions if you have them. Here's what we have. So f of x can be thought of as x squared plus 1 to the half power. So when we talk about f prime of x, we would have 1/2 times the x squared plus 1 to the negative half power times a 2x, which when we simplify it just a little bit, we end up with x times x squared plus 1 to the negative half power, which I can think about as x over x squared plus 1 to the half power. Okay? So then I use that and find a second derivative. So I can go ahead and try to find a point of inflection. Okay, so low d high. So low d high minus high d low over low low. Okay. And now we get back to my favorite part of this, the simplifying, where I can flex on my factoring strategies. So here's what I see in the numerator. I see the x squared plus 1 that they both have in common. But I also see they have different exponents. So I'm going to choose to take the one that has the negative 1/2 because that's going to guarantee that the x squared plus 1 to the half power, it'll work out nicer that way. Okay? So just like I've been doing all semester long. If I pull that out, I end up with x squared plus 1 to the negative half power. That means I would end up with an x squared plus 1 minus x times an x, because this 1/2 and this 2, 1/2 times 2 is just x, so that's where that came from, over, and same idea, 1/2 times 2 is just 1, so it would just be x squared plus 1. Okay? And then taking that and simplifying it, oh boy, we end up with x squared minus x squared, so we end up with 1 over x squared plus 1 to the 3/2. Okay? So this is a very strange example, but that's fine. We'll still go through it and talk about what we notice. So here's what I'm saying this is strange. If I'm trying to find the point of inflection, I need to find out where the second derivative will either equal 0. Did it again. where the second derivative will equal 0, or when the second derivative does not exist. So what I usually do with that is I take that to mean this. Set the numerator equal to 0 to figure out where the second derivative to figure out when the second derivative will equal 0, and I take the denominator and equal to 0 to figure out when the second derivative does not exist. However, if I look at the numerator, 1 equals 0 means I have no solution. So my best bet is going to come from the denominator. So I'm trying to figure out when x squared plus 1 to the 3/2 power will equal 0. Which really means I'm trying to figure out where x squared plus 1 will equal 0. Which means I'm trying to figure out x squared has to equal -1. So that does not yield a real solution. Okay, did all that work, got here, so that makes my job easy. Because if I don't have a point of inflection, that means that this graph never changes concavity. So if I can figure out when, like if it's going to be concave up or down just by using the second derivative, then I'm pretty much done. So I'm not even going to bother drawing the number line because there's no point of inflection. No matter what I choose, it'll tell me what I have. So since the second derivative came out to this, okay, I'm going to go ahead and plug a number in. Let's say 0, because 0 is a super nice number. F double prime of 0 would give me 1, which is positive. So because there are no points of inflection, and I just found my second derivative gives me a positive number and will always give me a positive number, I can say that from negative infinity to positive infinity, since there were no domain restrictions on this function, that's why I use the infinities. F of x is concave up. All right. Okay, so now that we did a hard one, let's do something a little easier. So be like, oh my gosh, that was too much, and not today. So let's clear all. Let's go home. Thank you. Okay. So let's say we're looking at f of x will equal a negative 3x to the 5th plus a 5x cubed. Okay. So first things first, we need to get our second derivative, and we need to do it kind of quickly. So f prime of x will equal a negative 15x to the 4th minus plus a 15x squared. Okay, so then the second derivative should be negative 60x cubed plus 30x. Okay. So, same idea. I want to figure out my points of inflection, so I need to figure out these two things. Either when f double prime of c will equal 0 or where f double prime does not exist. However, I have a polynomial. Polynomials always exist. So the second possibility for a plane of inflection doesn't apply. I just need to figure out when this will equal 0. Yeah, let's do it. So I'm going to do some factoring. Let's make it a 30x. So then we have negative 2x squared plus 1 should equal 0. Okay. So based off that, I think I have 3 inflection points. So from here, I could say x is equal to 0. And from over here, yeah, let's stay green. I want negative 2x squared plus 1 to equal 0. So that means I want x squared to equal a 1/2, which means I want x equal plus or minus square root of 1/2, which doesn't help me written this way. So I'm going to say plus or minus radical 2 over 2. Look at that. It's not even trig, but here we are. So I now set up my number line with these 3 inflection points, and I need to test out to see when the concavity changes, if it does. So here's what I shall do. Set up the number line. Move this John up. I have 0. I have negative radical 2 over 2, and I have positive radical 2 over 2. Okay. Cool. And I also have my derivative, which is right up there in the yellow. So I need to do some testing. I am going to choose, square root of 2 is a number bigger than 1, but it's, square root of 2 is a number bigger than 1, so when I divide it by 2, I should have a number less than 1. So I'm going to say negative 1. And if you can't do what I just did, feel free to use a calculator. Okay, oops. I should note that at these green values, these are equal to 0. Okay, so if I plug a negative 1 in for x, 30 times a negative 1 will be a negative number. So this will be negative. Negative 1 squared is positive. Negative 2 times 1 is negative, plus 1 will remain negative. So negative times negative gets me a positive. Okay. Let's see, I gotta choose another number. So I will go with negative 1/2. Yeah, because I could write that as square root of 1, and square root of 2 is bigger than square root of 1. So that's how I know that that value would fit in that spot right there. Okay, so 30 times a negative 1/2 would give me a negative number. When I plug the negative 1/2 in, I would get negative 2 times negative 1/2 squared plus 1. So it would be negative 2 times a quarter plus 1. 2 times a negative 2 times a quarter would give me a negative half, plus 1 would make it a negative number. Oh no, it would make it a positive number. So negative times positive gets me negative. And now I'm going to kind of mirror that. I'm going to have a 1/2 here. Okay. This will be positive, and this will essentially be the same thing because half squared is the same thing as a negative 1/2 squared, so it's positive times positive, so this is positive there. Okay. And when I look at the last interval, I'm just going to choose a positive 1. Okay. that will be positive. This will be negative. So this will be negative. So as a result, here's what I can say. We call these points of inflection because they should be written as a coordinate point, right? So I should figure out what the following coordinate points are. Negative 2 comma 2 parentheses f of negative 2 comma 2 is a point of inflection. That's where my concavity changes. 0 comma f of 0 is also a point of inflection, and same with radical 2 over 2. F of radical 2 over 2. It's a point of inflection. As the name states, it has to be written as a coordinate point. Right now, I'm satisfied taking these as answers because that's good. So I have my points of inflection, and here's what I can also say. Yeah, let's do it in red. From negative infinity all the way up to negative radical 2 over 2, or from 0 to radical 2 over 2, f of x is concave up. From negative radical 2 over 2 to 0, or from radical 2 over 2 to infinity, f of x would be concave down. And that's it. That's the same idea we were doing with the interval testing. Good luck.